Hello, my name is Jingonelli, and today we are going to be looking at sampling distribution. So for today's tutorial, we are going to be merging up with Madam Aciro's lecture, the Bstat lecture that was live. So I'm going to take you through the first parts that weren't recorded. So this was a top request by one of the subscribers, that is Mohozi Martin, from one of the MOOBs branches, that is Bara campus. So Mohozi, hoping you leave a comment after this tutorial, check whether you have got it and you have understood. So with sampling distribution, the major objective of statistical analysis is to know the true values of the population parameter. I remember population parameter, when we are beginning of statistics, this is just the numerical value that describes the characteristics of the whole population. And we had examples of, for example, population mean, and the saying in general, a single sample is taken and its statistic is considered to represent the population. So, however, to use the sample statistic, and you remember from sample statistic, like a statistic is a numerical value that describes the characteristics of a sample. For example, sample mean. We are going to be looking at this. So to estimate the population parameter, I was saying, however, to use the sample statistic to estimate the population parameter. So I want to use a sample statistic to estimate the population parameter, and I've looked at the two definitions. So we should examine all the possible sample of the sample size. So from the population, so we should examine all the possible sample of the same size from the population. So because a single sample may not be a true representative or representative enough, i.e. if a single sample is taken from the population, the sample statistic, that is sample mean, the sample deviation, standard deviation, may not be the same as the population parameter, which is to do with the population mean, population standard deviation. So if I told you had to take a single sample, so meaning that you won't get correct things. So if it were possible to take all the possible samples of the same size from a given population, then the distribution of these samples would be called the sampling distribution. So we are going to be looking at the sampling distribution, and this is what we are looking at as our topic. So if we compute the means of these possible samples, then the distribution of the mean of the samples is referred to as sampling distribution of the means. We are going to be looking at this. So we can illustrate this using an example below. So here they have given you something as an example. Suppose a lecture gave a quiz to a small class of just 4 students. You can see this is like the population, and the results of the quiz were 2, 4, 6, and 8. So the population mean is, so population mean will be 2 plus 4 plus 6 plus 8 divided by 4, giving you a 5. So assuming this is our population mean, and it's a 5. So the population standard deviation will be got by this formula, summation of brackets, that is x minus mu, which is to do with the mean of the population, divided by n. Make sure this is in brackets squared. So once you do this, divide by 4, you will get your standard deviation as 2.236. So once that is done, now let's take all the possible samples of the size n. That is, if I told you we are taking 2 from the population of this with replacement, and compare the mean of the samples. So we want to compare the mean of the samples. Now this right here, is a continuation of the first one. So it should be from 2 and 2 to 8 and 8. So if I'm to take samples, remember I'm taking 2, 4, 6, 8. So if I'm to start off with 2, 2, and I take 2, 4, 2, 6, 2, 8. So all the 2's are done on that side. The ones that are beginning with 2's, I'm done with them. Then I go to the next one, which is 4. So I go to 4, 2, 4, 4, 4, 4, 6, 4, 8. Then with the 4s, the ones that begin with 4, I'm done. So we go to the next one, which is 6. 6, I say 6, 2, 6, 4, because I already have the 6, 2 already here. So I go to 6, 4, 6, 6, 6, 8, and I'll be done. So the 6s are done. So I go to 8. 8, I have 8, 2, 8, 4, 8, 6, and 8, 8. So if I want to determine this mean is got by saying 2 plus 2 divided by 2. You get 2. Then for these 3, I'm going to say 2 plus 4 divided by 2. I'm going to get 3. Then for this one, 2 plus 6 divided by 2, I'm going to get 4. Like that. So this is how they have gotten these means. These 2, 3 up to 8. I told you this table, due to space, we made it go this side. Like this is how we did it, but it's a continuation from 2, 2 to 8, 8. Hope that's clear. So if we are to use the first sample, now imagine if they are to use the first sample, its mean is 2. That means it won't be a correct representative. And remember our mean was a 5. It's right here. Our mean was a 5. So we are having a 5 here. Our mean was a 5. So that won't be a correct representative. Even if we are to take, so if the last sample is the mean and the mean is 8, so that means both samples are unrepresentative of the population with a mean of 5. So they're not true representatives. But now let's organize the means of the possible samples into a frequency. So if at all we organize these means into a frequency distribution, using the frequency, like into a frequency distribution, and we say 2, how many times does it appear? So for 2, it appears only once. When you look at this and this, the mean, it appears once. How many times does 3 appear? This is 1, 2, and then yeah, there are 3. Sorry, there are 2. So 3 appears 2 times. Then we look for 4. How many times does 4 appear? This is one. This is the first one. This is 1, 2, 3. Yeah. Then 4 appears 3 times. Then let's look for 5. 5, how many times? 1, 2, 3, 4. So 5 appears 4 times, like that. So those are their frequencies. So you determine for 2 up to 8, how many times do they appear? And this gives you a total of 16. So then let's convert the frequency distribution into a probability distribution. So with this, you say, if at all I'm having my sample mean as this, from 2 to 8, then what is the probability of x? The probability of x is going to be 1. I'm using the frequencies. Remember, the total was a what? A 16. I'm going to say 1. Where's my cursor? It's here. I'm going to say 1 divided by the total, which was a 16. Once you add all these, it gives you 16. So 1 divided by 16, the 2 divided by 16, then the 3 divided by 16, like that, till you reach this. And remember, with probability is always equal to 1. So when you get 1 out of 16 plus 2 out of 16 plus 3 out of 16, up to the last end, you're going to get a 1. Probability is always equal to a 1. So moving on, the probability distribution above is referred to as the sampling distribution of the mean. So this table right here is called the sampling distribution of the mean. So once that is done, then we look at the sampling distribution of the mean is the probability distribution of all possible sample means of a given size selected from a population. Hope that is clear. So we're having properties of this. We're having properties of the sampling distribution of the mean. So property number 1: the mean of the sampling distribution and the mean of the population are the same. We look at it. Remember, our mean was 5 from the other population we had. This show it to you. Remember, this is the true representative of the mean of the population, which is 5. So they are saying if I told you get all those samples, so it's here. They're saying the mean of the sampling distribution and the mean of the population are the same. So we get to look at it. So if I told you get the x, that is 2 times 1 out of 16, you're going to get 0.125. Then if I told you get 3 times 2 divided by 16, you're going to get 0.375. And once you add all this, the summation of the summation of x, probability of x is equal to 5. So this is what they mean. The mean of the sampling distribution and the mean of the population are going to be the same, and this is what I have done here. So that is that with that. So property number 2, the standard deviation of the sample means is smaller, is already smaller than the standard deviation of the population. So meaning these ones of the sample, the standard deviation will always be smaller, and the standard deviation of the population will always be large or bigger. So this one is going to be smaller. So once you say standard deviation of the sample means is equal to square root this, and you compute all this, then divide by n, and you do this, you're going to get 1.581. But you're getting 1.581. But remember, for the other population, which was having a mean of 5, the standard deviation, the population standard deviation was a 2.236. So don't you see that this one is bigger, the population standard deviation, and for the sample means it is smaller, which gave us a 1.581. So what does this show? It shows that there is a standard error of the mean, meaning that this is not a true representative. So it will mean that this one, the sample means, the standard deviation will always be smaller. So the standard deviation of the sample mean is called, so this is also called the standard error of the mean, which is represented by sigma, then sample mean. So this means the x bar, the small x bar represents the sample mean. So it will mean that this will result into a standard error of the mean. It won't be like a true representative of the real population standard deviation. So, and it is so here they continue and say, and it equals to the population standard deviation divided by the square root of the sample means, and it's given by. So this is another formula which you can use, and a way easier formula you can use to determine the standard error of the mean. So you can just say standard deviation of the mean or of the sample means is equal to sigma divided by square root n, which represents the sample size. And hence, once you get the once you get this standard deviation, which you will pick from here, let me show you standard deviation. Yeah, so this figure here, the population standard deviation, if I told you having the population standard deviation, it's what you will come and impute here. That is the 2.236 divided by the square root of the n, which will give you a 1.5. So still it will give you the same answer. So 1.1581, it will still give you 1.81. So that is that with the standard error of the mean. But having used so these two can give you the same answer. These two formulas here, they can give you the same answer. So having used that, remember they are not the true representatives, but we are having something that can try to minimize this standard error. We are having something that can somehow minimize the standard error of the mean when it is not too small, at least. So with that, NB, the standard error of the mean, can be computed from the following formula above. But if the mean is finite and we know the population, hence standard error is computed by the formula. So at first, if at all the population is finite, in that you know the population, you know the exact value of the population, and that means you know the population mean. So with this, if at all you know the population value, you can use a standard error. Standard error will be computed as this. It will be the sigma divided by divided by the square root of n, and remember the and remember so remember the this fact the what it is multiplied with, yeah, is called the finite correction factor, the one which will try to minimize the error, the one which will try to minimize this standard error of the mean. So if at all you want to reduce it, that's when you multiply it with this finite correction factor. So you will just get this you'll just get the standard error of the mean, which is this, times the finite correction factor, which is this, represented by this, which is square root of n minus small letter n divided by n minus 1. So once that is done, this represents the population standard deviation, this represents the population size, and n represents the sample size. So that is with that. So you can use it in two ways. When you want to correct the sample, when you want to correct the standard error of the mean, like you want to minimize it, and also when the population is finite and we know the population mean, you can use this formula. So that is done. So you know that this here is called this factor is known as the finite correction factor, and should be used when the population size is finite. So it is known, yeah. So however, most times we deal with very large populations which are considered infinite, and if then we assume this, that is the brackets n minus capital letter n minus small letter n close brackets divided by open brackets n minus 1 close brackets, would approach to 1. Hence it will just be, because it will be now a 1, it will be this standard error, the standard error, it will be the standard error of the mean, times the 1, which will still give you this. So this is what they mean by this explanation. You can get any figure which is like having very large population, and you start to substituting, you realize that it will somehow approach itself to 1, which will just because when you apply the square root, still you get 1, and then you just multiply with this, and you will just be left with this. So leaving that aside, we go to the shape of the sampling distribution of the means. So the shape of the sampling distribution of the mean tends to be bell-shaped. It tends to be bell-shaped in a way that, let me show you something here. You know how a bell looks like. So once you look at the frequencies here, are you seeing that we are going to be, I want you to imagine how a bell looks like. It's having a bottom which comes upon rising, and it's having a peak. It's like a hill. So you can see it's rising 1, 2, 3, 4. Then it reaches its peak, which is a 4. Then it starts going down near the other side of the hill, which is now 3, 2, 1. Are you seeing that? So that is what they usually call a normal distribution. It's having a bell-shaped. So here you can come and say, with this is another property, the shape of the sampling distribution of the means tends to be bell-shaped and approximates the normal probability distribution. So it somehow approximates the normal probability distribution even when the population is not normally distributed. You get? So I've showed you how it looks like. It's like a bell. It goes it starts from the bottom, then it goes up. Its peak was for like a hill. It will be like a hill. So that's the bell-shaped meaning. So this is what they call the central limit theorem. So the central limit theorem states that regardless of the shape of the population, the distribution of the sample means approaches the normal probability distribution as the sample size n increases, and with this sample size n increase, what do they mean? NB, for the distribution of the sample means to approximate the normal distribution, then the sample size should be large, and this is having n greater than or equal to 30. So if at all you're having n greater than or equal to 30, that's when you use the Z table. You get? And if at all it is less or equal to 30, if at all it is less than 30, that's when you get to use the T table. There's another table called the T table. You can use Google, you can download it and maybe try to see how it looks like. So, however, it should be noted that the sampling distribution would be normally distributed if the sample means from a normally distributed population, no matter what the size, the sample, no matter the sample size. So here, the central limit theorem can be used to answer questions about the sample mean in the same manner as a normal distribution. Remember, for a normal distribution, they also use a Z somewhere, whereby we use some Z tables. So is used to answer questions about individual values, except that the new formula is used for Z. So here, remember, with the normal distribution, we get to say like x bar minus the mu divided by the divided by the sigma. So with this, the new formula, we are going to add something which is going to be Z will equal to, that is x bar minus the mu divided by the sigma. Then again, I divide this sigma with the square root of n. So that is the addition there. So it is slightly similar to the normal distribution, but the formula changes for Z. And then I will be using the Z tables. So an example here, they're saying IQ scores of students in a certain college are normally distributed with a mean of 120 and a standard deviation of 10. If a random sample of 25 students is taken, what is probability? The mean of the sample will be between 120 and 125. So allow me to end here so that we can merge up with Madam Aciro in as requested by that is Mr. Mohozi Martin from Barara campus.
Equals to, remember we said the difference between this and the normal distribution is that this is standard, it is the sampling distribution of the means. So we get our Z as x bar minus mu divided by sigma over the root of n. So now in that case, we have Z will now be equals to the mean or the value of x. This one's supposed to be x bar. It was supposed to be just x. Just grab this a bit. This is supposed to be x.
Excuse me, madam.
Yes, please.
Is there possible we can get this video after the lecture? Because some of the things I've not gotten them from up there and would to catch up.
Are you guys serious? You've not got me seriously. I thought we've been together all along.
Yes, but still a recorded video would mean a lot to us. Please help us.
We are following, but the video matters a lot for a better recap, madam. These things need a better follow-up.
But does MOOCSEP record, does this recording come automatically? Can you find it on MOOCSEP automatically, or someone must have been recording?
They have already told us they record, but we have never seen any record.
Sure. Nelly, is Nelly on call?
Yes, madam.
So what do we do here? Is there somewhere, has there been a recording before, like for these lectures here, or we needed to have recorded by ourselves?
Administration has to record something, the one which issued the link. But I don't think they're recording because we're not having a host. So maybe I'll improvise somewhere. But basically, starting from this example, they'll explain somewhere, then I don't know. From there, they'll be maybe able to understand.
So you guys mean like you've not been hearing only from this example or from?
So, some of us got issues just like you had gotten issues before.
Network.
Yes, so some of the things we could not get to them like that.
Now what are we going to do? It's tough, eh? Okay, but we'll always find a way. We'll always find a way. Okay, so what I was trying to say here is in the formula, instead of x bar, we're not supposed to have x bar. It's supposed to be just x, okay, as the value of the IQ squares for which you want to find probability in between it and then the mean. So that value is 125. So we are looking at the area or the probability between 120 and 125. So what we do, the x value would be 125, and then the value of the mean, which is mu, is 120. So we subtract the two. I think I'll first make some adjustment in the notes again, and then I share new notes to you people. You could use what I sent before, but I'll send new ones with correct adjustment. Some of these things were an oversight. Okay, so here we're seeing 125, which is the value of x. Then we subtract the mean, which is 120, and then we divide by the standard error. So at the end of it all, we get our z value as 2.5. So now z is the number of standard deviations that a value is from the mean. Every time you see z, z stands for the number of standard deviations a value is from the mean. So now we can then get the probability that a value will fall in between 120 and 125 from what we call the Z table, what we call the standard normal distribution table. I told you people to get it earlier. So I think I have it somewhere here.
My wife tells me I'm going that beautiful woman.
Ani?
Muozi.
Mukazi we?
Anange, people talking about
mukazi we.
I know the most beautiful woman on earth. Today you drank the whole day.
MC Ronnie, please forgive us. Let us finish the class in peace.
Bobby Wine yamuyitako mutami. And yali agamba Museveni and this drunk son.
Okay, people, if you have the table, the standard normal table, let's get that table. And then we read the Z value of 2.5. Do we have the table as I advised earlier on?
Yes, madam.
Do we have it?
Yes, madam.
Okay, so let's go and read the probability of Z equals to 2.5. I hope we know how to read that table. But you did the normal probability distribution.
Which table do we use?
The standard normal, I thought I'd actually downloaded it and attached it here, but I don't seem to see it. So it is called the standard normal distribution table. It's the Z table. On top of the table, you see Z. Z table. Let me try to check if I have it here. Okay, I have the table there. Let me share it so that we can see. Where is it? It's right here. Let me share the table. Are we seeing it? Are we seeing the table?
Yes.
Yes, madam. Yes, madam.
Okay, let me just maximize it.
Yes, madam.
So that is the table what we call the standard normal distribution table, or what we call the Z table. So now that this table here gives us the area or the probability between the mean and a given value of Z. In other words, between the mean and a given number of standard deviations. So from our computations, we got the value of Z to be, what was the value of Z again? Was it a 3?
2.5.
What was the value of Z?
2.5.
It was 2.5. Okay, so it means 125 is 2.5 standard deviations from the mean. Our mean is 120. So now we look at the area in terms of the number of standard deviations. So when we come to this table, we would realize that there are 2 columns in this table here. There is the vertical column, and then there is the horizontal column. Are we seeing that? So now the horizontal column, I mean the vertical column, reads 1 decimal place. Do we see it's reading only 1 decimal place, 0.1, 0.0, 0.1, 0.2, and so forth? Whereas the horizontal column reads 2 decimal places. So if we wanted to read the probability of, if we wanted to get the probability of Z equals to, let me say, 0.0. 0.0 would not make sense. Let me say 0.10, 0.10. So the first 2 digits, that is 0.1, would read it vertically. So we'd look out for 0.1 vertically. Have we seen that? Have we seen 0.1? And then we come and now look out for the other values remaining. That is 0.000 horizontally. So now we look out for the intersection of 0.1 and 0.0. The intersect, are we seeing the intersection? Where they meet at 0.0398. Do we see that? Okay, let me bring in another value. What if we are looking out for the probability of 1.25? We want to read the probability of 1.25. So what we do, we look out for 1.2 vertically. Are we looking out for 1.2? Let's go down vertically, we'll get 1.2. Have we seen 1.2? But we realize that when we have read 1.2, we shall remain with another value that we have not yet read. So 1.25, if we have taken 1.2, then we'll have 0.05 left. Remember, let's follow this. Let's follow this. We are looking out for the probability of 1.25. Okay, so we say the first 2 digits, the first decimal place, that is 1.2. We read it vertically. We look out for 1.2 vertically. So we find it there. But then when we have read 1.2, if we have removed 1.2, then we'd realize that we shall remain with other numbers, that is 0.05. Are we together?
Yes.
So now we get 0.05 now horizontally. Are we there? So we come to the intersection of 1.2 and 0.05. Which value do you have in the intersection of 1.2 and 0.05?
0.3.
I hope you're seeing my cursor, how it's moving. So we have 0.3944. Okay, let me give you a task. Can you read the probability of 1.59? 1.59. You read that and you let me know what you get.
It is 0.4441. 0.4441.
So we see how easy it is to read the table. Okay, so now let's read and we get our answer. Let's get the probability of Z, 2.5. Let's download this table. Let's download this table after. Okay, so what do we get? 2.5. What are we going to do? How are we going to read 2.5?
2.50.
Yes?
2.50.
It is 0.4938.
0.4946.
2.5. So you're going to read 2.5 Thank you. You're going to read 2.5 vertically and then 0.000. In other words, we're saying if we have 2.5 and then we remove 2.5, then we'd remain with 0.000. So what you remain with is what you read horizontally. So what do we get? This is 0, 1, 2, 3, 4, 5. Is that what we get? 0.4946?
Yes.
That's what we get.
Yes, madam.
Okay, so that is the value, the probability of Z. So now we go back. We go back. Let me just share again. Where is it? Sampling distribution. Okay, so now we go back and then we find the area for Z equals to 2.5 as 0.4938. Is that the value? We read 0.34929.
You read something.
Wrong.
Let me first go back there again.
Madam, what you read was wrong.
Let me go back again.
0.49.
Because now I'm not seeing what is up there. This is 1, 2, 0, 1, 2, 3, 4, 5. It is 4946, not so?
Yes.
Okay, so we can go back and correct that. Go back and correct that.
Madam, first explain more about that.
Madam, the answer is 2.5, then you have 0. That's the correct.
Madam, can I ask a question?
Yes, please.
I thought if it's, for example, if it was 1.23, you would look for 1.2. Then you go and then you go look for the 0.03 on the, is it the x-axis?
Yes, dear, yes.
Yeah.
Yes, but now if it's 2.5, can't you just stop on the 2.5?
Ah, we are looking for 2.5 and then 0.00 horizontally.
Yeah.
Thank you very much. I was again looking for 2.55.
No. Yeah, now that's why we're getting confused.
Yeah. It's supposed to be 2.5 vertically and then 0.00 horizontally.
Yeah, that's what I was thinking.
Yeah, that is right. I was having the value 2.55 in my head. Sorry about that. Okay, so let's go back there. So our answer was correct. 8. Yeah, that is the value. So that is the probability that the IQ square will be between 120 and 125. So what does that value mean? We're saying that it shows that there is a 49.38% chance. So probability, ladies and gentlemen, can be expressed in so many ways. You can express probability in percentage, you can express probability in ratio, you can express probability in fractions, okay? So even if we have a percentage here, it is still the same thing. Are we together? So we're saying there is a, yes, please.
I don't know whether I'm the one confusing the two. When you read 2.5 here on mine, it is reflecting what you were reading of 0.49.
Okay, let me share again so that we clear that. Okay, so you're looking out for 2.5.
2.5.
Let me explain.
Yes.
Yeah, let me explain that again. So we said if you're looking out for 2.5, that is just one decimal place. It means you're going to look for that 2.5 vertically. So we look for 2.5 vertically, we come and we find it there. We have seen it, eh?
Yes, madam.
So 2.5 minus 2.5, what do we remain with? So if we have already read 2.5, it means we are going to remain with 0.00, isn't it? So the 0.00, we now come and read it horizontally. So this is the column for 0.00. We are seeing it. So now we look out for the intersection of 2.5 and 0.00. Then that is the value. That is where they intersect, where they meet. They meet at 0.4938. Is that right?
Yes, madam.
Yes, madam.
All right, so that is how it is. That's how we read it. So we can go back again to our share. Yeah. So there is a 49.38% chance that the sample will fall between 120 and 125. So in this example, we note that the population is infinite. We do not know the population. That's why we took the standard error as sigma over the root of n. Okay, so let's try out this other example, ladies and gentlemen. Let's try out this example. The height of 1,000 university students is normally distributed with a mean of 65 inches and a standard deviation of 3 inches. If a random sample of 25 students is taken, what is the probability that the mean height of the sample will be between 67 and 69? The procedure is the same. The only difference is that this population is now finite. We know the population, so we have to correct the error by using the finite correction factor. So can we try that? Or you can try that later.
Let's try.
No. Someone is saying no. If I were you, I would actually be excited to try.
We try together.
Okay, so we start the first step. We said we first illustrate that on the normal distribution. So we draw the normal distribution curve, come to the center of it, draw the mean. The 67 is the mean. I've not put the mu such that you also know that even if you have not put the mu, in the middle there is the mean. So they say the mean is 67. So we put the mean there. And then they are telling us what's the probability that the mean height of the sample, remember here we are still talking about mean of the sample, will be between 67 and 69. So we said if it were a graph, then we'd start listing the values from 0, 1, 2, 3, 4, 5, 6, up to 67. So it means 69 would be a value after 67. We put it there. So the probability they want us to find is between 67 and 69. Are we there? Just the same thing we did before. Okay, so now we come and get the number of standard deviations that 69 is from 67. That is Z. I told you Z is the number of standard deviations. But the population is finite. So if the population is finite, what do? We get the standard error of the mean. Sigma x by standard error of the mean. We get it as sigma divided by root of n times the finite correction factor. Are we there? So we do the correction. We do the correction. I don't know why this went down. Let me just take it there. So we do the correction. We come down and say standard error will now be the standard error of the mean will be standard error times the finite correction factor. So our population is 1,000. The sample size is 25. We divide by population size minus 1. So if we do that, then the standard error of the mean would be 0.592. If anyone is actually pressing the calculator, please correct us if that value is not true. Okay, so that means our Z now would be X minus mu divided by sigma X bar. Sigma X bar, I said, is the standard error of the mean. So we'll come and get the X value, which is 69. We subtract the mean, and then we divide by the standard error of the mean. So if we do that, someone help us. What do we get as the value of Z? What would be the value of Z? Someone please help us. 69 minus 67 divided by 0.592.
3.3.
It is
3.38.
3.38.
3.378.
3.378. But remember, our table is giving us only 2 decimal places, yeah? So most times you make sure you round to 2 decimal places, the value of Z. Okay, so now let's go and we read the value of Z equals to 3.38 and we see what we come up with. Let me share that table again. Okay, let's go ahead and we do that. Let's read that.
It's 0.499.
Let me go to, do we have it up to 3? Our table stops only on 3 doesn't go up to 3.38. Doesn't go up to there. 3.38. That is now a challenge. I think I should have used a value that is smaller such that it can fit.
I thought maybe for each values, the range is from -3 to +3.
No, with the law of symmetry, a negative is the same as a positive, yeah? So the same table is used whether the value is a negative or the value is a positive. Okay? The law of uniformity, the law of symmetry, a negative is the same as a positive. The negative just shows us the direction. So the table is just stopping at
Madam,
3.
we can still get the figure using a calculator in case someone has the Casio calculator. If anyone has, then I can show you how it's gotten.
You first
value
tell
of
us
set.
how to get it using a calculator.
You press mod.
Mod?
Yeah, so where you see the value of SD, standard deviation. SD.
Yes,
Is it a 1 or 2?
it's a 1.
You press
Pardon?
1.
Pardon?
So after pressing 1, I want you to press shift.
Shift.
Then you
Yes.
then you come to 3, where you see distribution on 3. 3, shift 3.
Yes.
Then it has brought you P, then into brackets 1, 2, and that.
Yeah.
So I want you to press 1.
1.
Yes. So input your figure. What has it brought for you?
I put 3.38.
Differentiation.
Sorry?
I put 3.38.
9.
Yes. 3.38.
So 0.99.
Yeah, that will be your value for Z table.
Okay.
Yes, mister. Let the class know how you did that.
Apparently, I don't have a calculator with me.
Madam, you said.
But I said, like, you go to mod, then you look for a function of standard deviation, SD. It is 1.
People with
Then
those calculators, please record that process. It may help you.
Some calculators don't show, but Casio FX it shows. Yeah, you go to mod, then you look for a function SD, standard deviation. Then you press the value they put for you down, either 1 or 2, you press that. So after pressing that, you press shift. Then you also press 3, which is the distribution function. So after pressing 3, you input the figure you want to read on your Z table.
That
then
is now
after
the 3.38.
Yes, then after you press enter, so it reads for you that same value on the Z table.
Thank you very much for sharing the knowledge.
Thank you.
Thank you. Friends, have you had that? You could utilize that. A table just stops at 3. Who is that gentleman? You can always contact him. Mr. I didn't even see who was speaking. Nelly, it was Nelly? Was that Nelly who was speaking?
No.
No, madam.
Who was that? It was Imran.
Imran.
Okay. Ladies and gentlemen, the calculator guy, the guy with all the skills there is Imran. You can always contact him. Imran Adams. Please,
Yes,
you
madam.
share your knowledge with the class. You share your knowledge with the class.
All right, no problem.
Thank you very much for sharing that. Colleagues, we can always do that. If you have any addition, anything that you know, I may not be in know of it, but you know, you can always share with us. Thank you very much.
So, madam,
Excuse me, madam.
Mean that we don't need now a distribution, this standard normal distribution table? If we have this?
No, the value that we have computed is a value that is not inclusive or is not included in that table. That table just stops at 3. Okay, only 3 standard deviations. So someone has come up with an option that actually we can't read that value from the table, but we can use a calculator and come up with that value. Yeah. Okay. So now you have a trial question. You have a trial question there. You can use this question. So you can encounter just about any scenario that you encountered in the normal distribution, in the sampling distribution as well. So tomorrow you find where all the values are below the mean, some value is below the mean, another is above the mean. So you can always do those examples. So there's one example here. Maybe I think I'm going to add another. As I said earlier on, I'm going to share the notes again with you people. I will make a correction of a few things that was an oversight. So I'll make a correction and then share the notes with you people again. So when you receive the notes, please try out the questions that are there. Example 3, you can try it out. Okay, so I don't know if we still have stamina to start on another topic or...
Madam, I have a question.
We have now. Yes, please, dear.
Does that mean that you can get like maybe a Z value like 4?
Yeah, a Z value like 4. Okay, so now, ladies and gentlemen, let me just maybe say this. In a scenario where the value is above 3 and you cannot read that value from the table, you can always round off. Yeah, you can always round off. Like for us here, we had 3.38. So we could just round it off and read the probability of 3.00. Are we together? In a scenario where now you can't also use the calculator, maybe the process is very long for you, you've forgotten it, you can always round this off, okay? Instead of taking 3.38, you take just a 3 and read that from the table.
Madam, the other thing I've realized is that when you plug in like for the recent answer of Z of 2.5, where we got from our table 0.4938, the calculator rounds it to 0.5.
Yeah, some calculators, it means the setting of the calculator needs to be done again.
So that means if we use this way, we don't need the distribution table.
Yeah, you can use that, but make sure the settings of your calculator is correct. Your calculator is not set in such a way that it rounds off. Because now the other one is giving us 0.5 and yet it is 0.4938. So you check the settings of your calculator such that you get the correct value from the calculator, as well that same value can be got from the table. Okay, people, so I was inquiring, do we still have some stamina to continue with the last topic, or we schedule another day?
Schedule another day.
Another day. Madam, another day. The
So
brains
let's
are
do
exhausted.
But you people,
we are going to do Wednesday. We are going to do Wednesday in the morning using the group A link in the morning on Wednesday. So that
it's
we
fine,
can finish
madam.
up with the last topic.
It's okay.
So okay, thank you very much. Let me just make adjustments on these notes and I share again. Thank you for attending. Have a good evening. Okay, bye.
Bye.
Wait, man, how's this thing work on the calculator? Mine has refused. Jingo, Nelly.
What are you asking?
That thing over the calculator, how does it work, man? Mine is refusing.
Do you have a Casio FX?
Yeah. fx weighted to
Now
y.
you go to mode. Go to